All right, hello everyone. I am Gus Carlock. I am here from Elastic. We are the search AI company. And this talk is going to be about getting started with retrieval-augmented generation using Elastic. So I guess let's dive right into what is Elastic. Elastic is it's a database company, right? We build three products: search, observability, and security. And the main thing here is we really do use generative AI at Elastic. So in 2024, we were named one of the top 5 land graph agents in production. And I was on the team that made it happen. We developed some of the evaluation features, okay? So how many people here, I'm just curious about our audience, are students at IIT? Can you please raise your hand? Okay, now keep them up if you're majoring in computer science. Okay, so that's a large proportion. And now, how many people are not majoring in computer science? Okay, a few, we had a few, cool. And then how many people here are from outside of IIT? Awesome, so we have a few. So I'm gonna give you just a brief introduction to what is Elasticsearch. So Elasticsearch is an open source and distributed RESTful search and analytics engine. So what does that mean? Does anyone know, can anyone tell me what is Elasticsearch really good at? I'll give you a hint, it's in the name. Search, yes, we are good at search. So how many people here have used like a SQL database, like a columnar data store, right? Yep, and what are those good at? Those are good at like aggregations. They're based on columns, right? This is very different, right? When we're talking about this kind of data, we're talking about text data that we want to retrieve, okay? And the Elastic Stack is capable of addressing a growing number of use cases. So I think almost every company that I've ever worked at professionally has used Elasticsearch in some capacity. It's super common in industry. And the main thing here, again, it stores your data for lightning fast search and fine-tuned relevancy. What does that mean? Well, it's like you can retrieve the correct text data. You can retrieve the correct records, okay? And we also have analytics. And okay, so how about Kibana? How many people here have heard of Kibana? A few, okay, cool. So Kibana is like the window into the Elastic Stack. It's how you interact with Elasticsearch. It's how you get around, it's how you configure things, it's how you query your data, okay? So there are a few ways to get started using the Elastic Stack if you've never used it. Since we have a pretty highly focused CS audience, I'm going to dive a little bit into this, right? So one way is to use start local. And I actually have that here. Oops. Okay, we're in that folder. So all we need to do to use start local, there it is run this file, basically. So this is, if you go to this URL, it gives you this command, which will just download this shell script and run it. And then the only caveat here is you have to have Docker installed. So you go to the Docker website, you install Docker, and then you can run this command. And hopefully this live demo works. We'll see. Okay, well, it's already running, so I'll just go. I already ran it. Okay, well, we're not going to deal too much with that. You can figure this out on your own. First live demo issue. But the other thing here is, go back to the slides. We have a cloud offering, so you can sign on here to cloud.elastic.co. It'll start up and it'll run it in a few different cloud providers: AWS, Google, Azure, whichever one that you choose. and I'll start up the infrastructure that you need for this. Okay? So we're going to go through a little motivation here and just go over the problem, like the larger problem. What is RAG? How many people here have built a chatbot? Anyone? Okay, so a lot of people here are already familiar with this as well, right? But we can use Ollama, which is from Meta. It's very easy. You just download this as well, and then you can run it in the command line or terminal. So we'll start up Ollama. All right, and then I've written a prompt here. So the key thing here, right, is we start with some data. So this is based on the weather. This is just something I made up this morning. On January 16th, 2025, it was so cold that my beard froze when I was walking into the office, which is a true story. The weather in Chicago yesterday, February 10th, was cold and sunny, right? So these are just, basically what I'm saying is these are representations of different documents that you might have in your database. And I'm providing it with this information, which today's date is February 11th. So what is the temperature in Chicago today, right? Respond with an estimated temperature in Celsius, respond with a number. So I'm giving it some instructions. So this is essentially our prompt that we're giving it. This is some additional data. And then these represent the documents that are inside of our database. Okay? So I'm going to start up this model in Ollama, which is Llama 3.2. It's a very small model. It's like 2 gigs in size, so you should be able to run it locally on your laptop, and we'll see how it responds. All right, so it told me it's estimating that today it was -2 in Chicago, which it's below freezing, so I guess that's good enough. And we can also ask it things like, what was the, how about Jan 16? And it should tell me that. Okay, so it also gave us an answer there, which is totally wrong, by the way. So I will note that the free models are not as good as the proprietary ones that you can use. So anyway, back to the presentation. Right, so why RAG? And that is that these generative AI models have frozen knowledge, so they need recent data. Like here is an example from ChatGPT. I don't know exactly how old this example is, but it was before it was retrieving things from the web. So it says, who is the current president of the US? I don't know, but it was Joe Biden in January 2022. So that's obviously not relevant. But the other thing is it allows you to harness the power of LLMs on your private, organizational, or domain-specific data, right? So you have a couple things here. We might have a big collection of documents that we use for, let's say, our internal company purposes, like legal documents, or policy documents, or insurance documents, or any variety of things. Or we're trying to build something specific, like we're trying to build a chatbot that replies about music, or like musical artists or something. It might be better to use RAG because all that data might not be built into the models themselves. So why Elasticsearch? So as I mentioned before, Elasticsearch is great for retrieval and search. So it's ideal for this purpose. And it's highly optimized and scalable. So you can start really small, you can build something on your laptop, and then you can transfer this to a huge data set that's ingesting like millions of records. The other thing is we integrate with high performance models. We have high performance models of our own. I'll show you some of them. And like I said as well, it's open source. It's easy and free to get started. For some of the more for some of the better performance things I'm going to show you today, you do have to pay, but it's not anything unreasonable. Okay, so we're going to dive into the search aspect of this. So what is the difference between like a lexical search and a semantic search? Can anyone tell me? Does anyone know? Yes.
Lexical search is based on keyword.
Yes.
Semantic search is based on the sentiment.
Based on the meaning, right? Yes, okay. So let's say we have a character from a movie. Let's say we have Han Solo, okay? If we're trying to retrieve a document about Star Wars, right, and we put in Han Solo as our query, the idea behind semantic search is that it will retrieve those documents that have similar characters to Han Solo, okay? As where if you're just typing Han Solo in, you're just going to get specific records. So they're kind of different things, but they're both important to RAG. So Elasticsearch, our tagline used to be, for search, and now we've moved recently to saying, for vector search, because Elasticsearch is an excellent vector database. So how does this all work? I'm going to give you the big picture first, and then we'll dive into more of the details. So we start with some documents, but notably you can also use images and audio for RAG. But we get a vector representation of those documents, and then we perform a nearest neighbor search, okay? So what do we mean by like a semantic vector? So vectors can represent different things about our data. So in this case, we have one dimension here which represents a piece of data, whether it's realistic or cartoon, right? So the cartoon representation is toward 1, and the realistic one is toward -1, and this is just in one dimension. But you can represent many different things, right? So we can also represent human and machine on a separate axis. And so the idea here is that similar data is grouped similarly. So like we have here, like realistic humans, right? So these are realistic human representations. So if we have a new query, again, Han Solo, right? It's clear this is a realistic human. So this query would probably be somewhere here. All right, so I do want to dive in maybe a little bit more in detail here, but we'll get to that. So how do we get from our text, which we have given to the database, into this vector? Well, we have a wide range of supported NLP models that we can use at the database level when we're ingesting these documents. And the important one here, I don't know why it changed. The important one here is the text embedding model. So we support a couple of those. And we're going to start talking about Elastic E5, which is a dense vector. So that's kind of like I showed you before. It's numerical, right? So if we have Han Solo, we're going to convert it into some kind of numeric representation. And Elastic ELSER, which is a sparse vector, and we'll get to that a little bit more later. But you can also use any kind of vectorization model. OpenAI has text embedding 3 small. I think they have text embedding 3 large as well. You can use like open source models like BERT. You can use the embeddings out of those. So you can bring your own. So you can do this all inside of the ingest pipeline in Elasticsearch. Now, we have our vector representation of our data. So how do you actually search it? So like I mentioned before, the key thing here is you start with your data, which is just the documents themselves, and then you do the heavy lifting computations at ingest, okay? So basically when a user makes a query, you want it to be as quick as possible. You want it to return the results as quickly as possible. So the key thing is you vectorize it on ingest. Okay, so if you have a document, the idea here is you're not just ingesting it at this point, it also runs one of your machine learning models to get this vector. Okay, I'm going to pause there and see if there are any questions. Do we have questions yet? Yes?
So do we have a database of all these vectors pre-generated where this is getting matched and searched? Or?
Yeah, exactly. So the idea is like Elasticsearch is this database, right? And you bring your own set of documents. So maybe this is better. So these are specific documents, and they have a vectorized representation, right? So let's take a look at that for a second, actually. What does that look like? So this is the interface in Kibana, and we're just taking a look at a single record here. So here, this is like company policy documents. I had mentioned this as an example before. But you can see we have this vector representation. Now this is what's called a sparse vector, because each of the dimensions is a specific token, like a specific set of characters. This is the output like of a transformer model, so this is based on the vocabulary of that. And each of them has a value. All right, did I answer your question?
Yeah.
Okay,
So,
cool.
In that case, how is it different when you compare it with a search on a column, which is numeric?
Oh, well, that's sort of a different thing, right? So, but we'll get into like how to search through vectors. But yeah, you would just generally use like an exact match or a greater than or a less than if you're doing a numeric column, if that makes sense. Cool. Any more questions? All right, I think we're going to keep going then. Let's see. Back to the presentation. All right, so how does this actually work? Like, how do we search and retrieve these based on vector search? Well, probably you remember this from math. The basic way to take a distance between 2 points in space is Euclidean distance, and that's just the straight line distance, right? But we were talking more about semantic similarity, right? In multiple dimensions, so not only are we taking like just 2 dimensions, but frequently our vectors will be larger than 1,000 dimensions. And it turns out that cosine similarity, which is the angle of the vectors, is more important. Like the angle between the 2 vectors is more important, measured from the origin. And that's because the vectors have some sort of semantic meaning, okay? So if you take a look at, here's a few examples of cosine similarity. If you have 2 vectors that are close together, their cosine similarity is going to be roughly 1. If they're 90 degrees, which means maybe they don't, have that much in common, then they're close to 0. And if they're 180 degrees apart, that generally means that they're talking about opposite things, okay? And that's going to be -1. Cool. Now, kind of a more advanced thing, if you're into linear algebra, a better method of doing like dissimilarity is dot product. So that's just another way. And the reason why is because it captures information both on the angle and the magnitude of the vectors, okay? But before I get to that, I do have kind of one challenging question for you. Maybe someone can help me out here. Let's say that you have some random data. That are vectors, okay? And you normalize them. What does that do to the shape of the vectors, right? What does that do to the shape of this data? Can anyone tell me? Straight line? Nope. Well, a straight line, yes, but a straight line, how?
It reduces to same dimension.
Sorry, say that again?
It reduces to same dimension, all the vectors in the same dimension.
No, what does it do to the magnitude? If you normalize a vector, what does it do to the magnitude? It's 1. So that means that every dimension is 1. So what does it do to this data? Yes?
You'll have a circle.
Yes, you will have a circle. Okay, cool. So that was my challenging question. So you actually get, here you go, this is our company mascot. All right, cool. And then sort of a cool thing about that is now we have a circle here. So now, actually, for all of these points that live on this circle, the distance between them is equivalent to cosine similarity because it's the angle. So, right, if it's an opposite, it has like a maximal distance. And if it's orthogonal or 90 degrees away, it has the same distance. Cool? Okay. All right, so the key thing here is that if we have two similar vectors, we're going to call this the Han Solo vector. And then we have a Princess Leia vector. And we have a new vector that comes in. Let's say we have our Luke Skywalker vector, right? Where is that going to fall? It's going to be probably relatively close to these, right? So that's why this is called K nearest neighbors, right? So we're going to take, between Luke, we're going to take the distance between all the other vectors, and our two closest are going to be Luke and Leia, as where maybe like Darth Vader is somewhere down here, distant. Okay? And that's K nearest neighbor, and if you are implementing that at any scale, it's not really feasible to take the distance between every vector in your vector database. So there are algorithms like hierarchical navigable small worlds that allow you to take smaller like larger groups, it's a graph algorithm where you're taking and searching over a larger group of vectors, and it's coarse at the beginning, and it gets finer and finer. So if you have a query up here at the first layer, it's like blue. As it travels down layers, okay, it has to travel twice there, a couple times there, a couple times there, but you're not going over every record in your database, okay? All right, I should actually stop there for any questions. Do you have any questions on that? Okay, cool. So as I mentioned before, actually there's lexical and keyword search are also part of this picture. And with Elasticsearch, you can do both. So we have both a term-based score. How many people here know what TF-IDF is? Cool, so most people know. But basically, that's just going to give you a score, right? If you give it a query, it's going to give you a relevancy score. So that's a more classical method that's built into Elasticsearch as a part of something called BM25, which is just an extension of TF-IDF. And then we also have the vector similarity score. So that's basically the distance between your query vector and the vectors that are in your database. Okay, so we have like this way of scoring it, and then we use reciprocal rank fusion. That's a way of blending these scores together. As I mentioned earlier, we also have this elastic learn sparse encoder, which is one of our vectorization models. Let's see, so if you give a query to this, like these are not the droids you're looking for, you will get this kind of representation that's more based on like it's giving you actually the dimensions are specific tokens from the model, and then also scores. So if I go back to Kibana here, let's see, and I type in Mies van der Rohe and send it to there, we get this list. I'm going to go over to my demo and just run this quickly. So actually, this vector starts out with some smaller tokens, but you can see somewhere down here, it's knowing that he's an architect. So this is like capturing things about the semantic meaning. All right, let's go back here. Oops. All right, so bringing it all together. So again, we have like a query, and then it's going to go back, grab our business's data, and then it's going to pass it to the model, and then we get the right answer. That's the idea behind RAG. And I'm going to go back. So how many people here have used Jupyter? Okay, like almost everyone. Cool. So I'm not going to go into that. But there's a notebook here at this blog you can run if you want to get started. So it's using Llama 3. I showed that earlier with Ollama. And there's a link here where it's on GitHub, so you can go and run it yourself. So the first thing we do, obviously, is install the packages that are required. So I'm going to try to run this now, and hopefully we have better luck here. So the only thing you have to do is supply like authentication, like API key ID. So I've set that up differently than they did in the tutorial, but basically everything else here is the same. And then we're going to prepare our documents for ingestion. So I'm just going to run this. This is a JSON file that contains a set of sample documents. And it's going to, one of the things that it's doing here is it's splitting the documents. So what is like one limitation of neural networks? Let's say or transformer models. Let's say you're providing them with tokens. One of the limitations is that there's a maximum length that they can process called the context size. So it's important to split the documents into chunks, and that's what this is doing behind the scenes. And I'll show you that in a second. So we'll run this, and this will, let's see, keep going down. This will go ahead and store these with ELSER vectors. So we're creating a document store. This is something that was provided by LangChain that just obscures some of the details. This is what our documents look like. So each document has a name, a summary, which just describes the document, and somewhere down the line here, there's the page content. But I'm going to load this into the database because it's a little bit easier. All right, so go back to Kibana here. And this is our documents. So we created an index that's just a collection of documents. And you can see here, each has a vector associated with it, and then a set of text. And somewhere, you'll see that these have the same name, the first two, because it split this document into chunks. Okay? Let's go back here. And now we're going to actually do the whole RAG part. So we're going to instantiate Llama 3.2, which is like a very small model. Like I said, you can run on your laptop. And using these documents, we created a vector store earlier, and we're going to use them as a retriever. And this is going to use vector search to retrieve the ELSER encoded documents. So you can, we've given it this prompt, answer the question based only on the following context. It gives the context, which is the set of documents, and passes them into this model. And the question is whatever query we put into it. So I'm putting in here, what are the organization's sales goals? And we'll see what the retrieval and model give us. All right, so this looks, I think, pretty reasonable. And I pulled some more information from these, right, and I was looking, what else can I ask it? What are the requirements for a senior software engineer? And it's going to go to this data, retrieve the documents, answer the question. Cool? So I guess we'll pause here for questions. This is, yes?
Can I get a note? Where is the Jupyter notebook?
Yeah, so let me pull back here. So if you want to just take a picture of this, this is where the notebook is actually located. Yes?
I kind of have a question on chunking.
Yep.
Don't we kind of lose some, so we're chunking a book, and we're doing it by a certain number of characters, maybe that's like whatever half of the page. And don't we lose information that like this page was close to this page in the book?
Yeah.
And that's now.
Well, okay, that's a good question, actually. So I'm going to go back here. We'll take a look at this chunker in a little bit more detail. So this is a recursive character text splitter, and you'll see that the chunk size is set to 512. But then there's also this chunk overlap of 256. So what this is doing is if you have some text, it's taking this and making a chunk, but then it's also overlapping 256 characters so that you do have some matching context, so it's not splitting up entirely. Good question, though. Any more questions here? Okay, cool. I know it's getting late, so thank you for bearing with me. We're going to move on to next steps. What can we do better? So I think, yes, sorry?
How the data injection can be done
For
for updating data?
updating data? Yeah, so if you have new data that comes in, it's using the same pipeline. So basically what's happening up here is, let me go back to Elasticsearch, or sorry, Kibana. And we'll go up here. Oh, actually no, over here. So this is our index that we created. And if you take a look at the pipelines that are on the index, you can see that attached to it is the ELSER model. So as you ingest new documents, it automatically makes the vector. It automatically adds this vector field to the document. Cool? Yep, sure. Okay, so I think we have a pretty good general basis for what is RAG. So how can we do better? And the answer that we found is re-ranking. So one of the issues is, okay, you have vector search, you have BM25, you mix them together, but sometimes your results still aren't good enough to get a good response. So that's the idea behind re-rankers. So you'll start, right, let's say we have some documents. And I'm going to shade in. These are documents that have a relevant response, and the rest don't. So let's say this is your result. But ideally, we want to get to this, so that we're feeding only the most relevant documents in for generation. So how do we do that? One way is a re-ranker. So here's a couple examples of re-rankers. We have one called Elastic Re-Ranker, but there's another company, Cohere, that also has an endpoint for re-ranking. So this is just another way to improve the system, because RAG is actually very difficult in practice, right? It's easy for me to come here and tell you how to do the basics of this, but in practice there's a lot of tuning that goes into it to get a good result. And this is just another way to help you. Now, why not just pass all of your documents into a re-ranker? Anyone? Speed. So the key thing is what I've described with vector search, right? You can offload all that computation at the beginning. BM25 is very cheap to do in comparison to these transformer models. So that's why. Okay. All right, and I just want to say thank you to everyone who came out. My colleague Kirti and I, who's in Toronto, just also posted a blog here that's about how to do k-means clustering as an ingest pipeline with Elasticsearch. So if you're interested, go ahead and check that out. But yeah, if you want to contact me, here is my LinkedIn profile. So feel free to send me an invite or send me a message if you've built something with Elastic. I'd love to hear about it. So thank you. I really appreciate it.